Welcome to the course on Introduction to Electrical Engineering. We will discuss lecture 14 on resonance in AC circuits. Starting with outline of today's presentation, we will talk about of course introducing the resonance, then we will talk about phenomenon of resonance in various domains, and resonance in series RLC circuit. We will define the quality factor, then we will discuss bandwidth with the half power frequency, followed by we will discuss resonance in parallel RLC circuit. Then we will take practical parallel resonance circuit, which normally known as a tank circuit. So, followed by the ideal tank circuit and dynamic impedance versus dynamic resistance, and followed by some of the numerical problems like. Well, just to introduce it, we start with the introduction that resonance is identified with engineering situation, which involve energy storing elements subject to the forcing function of varying frequency, and resonance is used to describe the steady state operation of a circuit or a system at that frequency for which the resultant response is in time phase with the source function despite the presence of energy storage elements. Resonance cannot take place when only one energy storage element is present, either inductor or capacitor. Well, coming to this, if the inductance is analogous to mass and capacitance is analogous to a spring, then resonance only take place when two independent energy storing elements capable of interchanging the energy are present, like mass and spring, as you can see on the left side, and how it is the typically you can say the amplitude changes, position placement changes with respect to the time, or LNC, as you can see here the energy get exchanged between the either mass and spring or between L and C tuned circuit like. Well, although attention here is given to resonance in the electric circuit, resonance is a phenomena found in any system having two energy storage element, and resonance is observed in the following system: in a mechanical system, hydraulic system, pneumatic system, and the following are the some of the examples where the phenomenon of resonance is seen day by day life. A typical example of phenomena of resonance in various domains, starting from typically the resonance in electrical domain. So, it is used in radio frequency amplifier, as you can see here you have all the three elements, like especially the energy you have a capacitor and inductor along with the some of the typically resistive component of the part of the inductor or otherwise put separately like, but it is used for the purpose of course tuning the radio frequency corresponding to different stations like. Then you have a television signal. So, there we have a typically concept of resonance in electrical domain. Then we have a resonance in electrical domain, we use like in a spark gap transmitter and used in late 19th century for wireless communication, generated radio waves using electric spark and spark gap transmitters. Is used in typically resonance in electrical domain, especially air core capacitors in radio tune condenser, and simplified circuit of this, how we really tune this capacitor to change the frequency of the different, you can call it the station to which we can tune this typically our frequency of the radios like. Then the resonance in acoustic domain, the resonance in two tuning fork is demonstrated here. The force vibration lead to induced vibration in the other fork due to the resonance. Similarly, we have a resonance in acoustic. So, another example that acoustic instruments, it goes typically as a kind of resonance which gives you the typical kind of sign, and then of course, breaking of the glass using the sound wire resonance. You can just see how from the typically resonance that your glass is broken, or you have a typical resonance in this acoustic domain. Another example as a music system playing on the heavy beat, as you can see here how the typically the your sound system is just moving or having a displacement like. Then we have resonance in another example of acoustic system. So, vehicle acoustic resonators and acoustic resonance to reduce the enhance the exhaust sound or note. Then you have a resonance in mechanical system with the pendulum and force oscillation, harmonically driven pendulum. Then we have a resonance in mechanical system, resonance in swing set. Then we have a resonance in the mechanical domain as of the different kind of bridges like the force mechanical resonance leading to a bridge collapse. Then why to study resonance? So, resonance is the frequency response of a circuit or network when it is operating at its natural frequency called resonance frequency, and for many applications the supply defined by its voltage and frequency is constant. Example, the supply to residential homes is at 230 volt 50 hertz. However, many communication system involve circuit in which the supply voltage operates with a varying frequency, and to understand the communication system one require a knowledge of how circuit are affected by the variation of frequency. So, examples of such communication system are like a radio, television, telephones and machine control system. When resonance occurs and what it results in. So, resonance occurs in any circuit that has heavy energy storage elements, at least one inductor and one capacitor, and under resonance the total impedance is equal to the resistance only and maximum power is drawn from the supply by the circuit. Under resonance the total supply voltage and supply current are in phase. So, the power factor becomes unity, and at resonance L and C elements exchange energy freely as a function of time, which results in a sinusoidal oscillation either across L or C. And type of resonance we have like a series resonance or parallel resonance of the circuit consisting inductor and capacitor. Well, the resonant circuit series or parallel are used in many applications such as selecting the desired stations in radio and television receivers. The most common application of resonance is the tuning, that is as an oscillator circuit. A series resonant circuit is used as a voltage amplifier, and practical resonant circuit is used as a current amplifier. Parallel resonant circuit is used as a current amplifier, and resonating circuit is used as filters. So, example, now we have to take resonance in series RLC circuit. So, typical example we have a AC source and we have a series RLC circuit which have a series resonant, you can call it like that. Resonance is only when the reactance of the inductor is equal to the reactance of the capacitor, and they cancel each other, and the current is decided only by the resistance in this circuit. So, the resonance is the condition in an RLC circuit in which the capacitive and inductive reactances are equal in magnitude, and thereby resulting in a pure resistive impedance, and the input impedance is as follows. The circuit impedance Z equal to R plus j omega L plus 1 upon j omega C, which can be written R plus j in bracket omega L minus 1 upon omega C, omega L minus 1 upon omega C. At resonance the net reactance becomes 0, therefore, the omega r L equal to 1 upon omega r C, or we can say omega r equal to 1 upon under root L C in radian per second, and f r equal to 1 upon 2 pi under root L C hertz, where the omega r and f r the resonant frequency in radian per second and in hertz respectively. So, the reactance X L and X C versus frequency plot of this circuit. So, value of the reactance of the circuit is X equal to X omega L minus 1 upon omega C, which depends on the frequency, because both the reactants are function of frequency, and the inductive reactance X L equal to omega L equal to pi f L, which increases linearly with the frequency, and the capacitive reactance is X equal to 1 upon omega C, that is 1 upon 2 pi f C, which decreases with the frequency, and it is largest at lowest frequency. So, you can see the variation of inductive reactance with the frequency, it is increasing with frequency, and variation of capacitive reactance which is decreasing in magnitude with the frequency. Well, you can see the variation of inductive reactance with the frequency and capacitive. So, at F r X L equal to X C. So, the impedance Z is purely resistive, and below F r the X L is less than X C. So, the circuit is capacitive, and above F r the X L is greater than X C. So, the circuit behave as a inductive circuit. Well, how the variation of reactance and impedance with the frequency. So, you can say at resonant frequency F r at F r Z equal to R, and the power factor is unity, and below F r X L is less than X C. So, the circuit is more capacitive and the power factor is leading of the circuit, and above F r X L is greater than X C. So, the circuit is more inductive and the power factor is lagging in nature, as you can see here variation of resistance, reactance and impedance. The resistance remain constant, and typically the reactance of capacitance reduces and reactance of inductor increases, and X L minus X C goes from minus to plus, and where it becomes 0, you will find the impedance variation, I mean it is the minimum corresponding to resistance value at resonance. However, on other side, both the side, I mean the impedance is higher, much higher than what you have at resonance frequency. Well, we have impedance diagram. So, phase of the circuit impedance is given by phi equal to tan inverse X L minus X C upon R, and you can see the how the phasor diagram is there. So, at resonance frequency we have X L equal to X C and impedance is R, but at the frequency below, I mean the X C is more than the X L. So, you have not only resistance, but you have a reactance which is capacitive. So, there is impedance at the angle of phi, which is decided by the net reactance and the resistance of the circuit. Similarly, above F R, the X L is greater than X C, and you can see the net reactance is your X L minus X C is your typically positive, and along with the resistance you get the impedance. With the resistance it has angle phi, which is on positive side. So, you can call it below F R, X L is less than X C. So, phi is negative, the circuit is capacitive. At resonance, X L equal to X C and phi is 0, the circuit is purely resistive, and above F C, X L is greater than X C. So, phi is positive, the circuit is inductive. So, coming to current in the series RLC circuit, and the circuit current is given by V I equal to V upon Z at the angle of phi, or you can say V at the angle of minus phi upon Z, and that can be written as I equal to V upon under root R square plus omega L minus 1 upon omega C square, under root of that at the angle of minus tan inverse omega L minus 1 upon omega C upon R, because we are taking convention considering the omega L greater than 1 upon omega C, and the current is maximum when omega L equal to 1 upon omega R C, and when the circuit is resistive phi equal to 0. Therefore, I m will be equal to V upon R. Then variation of magnitude and phase of the current with the frequency. So, the current is maximum at resonant frequency, and the variation of magnitude of current and phase of the current with the frequency you can see here. So, here at resonance frequency you have a current maximum, I mean, and the phase of it is 0, because its circuit operates at unity power factor. But when you have a frequency lower, the current reduces, because impedance have a reactance also, capacitive reactance, and that reduces the current in the circuit, but the circuit behave as a capacitive nature. So, power factor is leading. Similarly, the if you go to the above the your resonance frequency, your circuit is inductive and power factor is lagging in nature, and typically the current also reduces, because along with the resistance you have some inductive reactance of the circuit like of this RLC circuit. Now, coming to another quantity defining like quality factor, which we define for energy storage element. So, sharpness of the resonance is in a resonant circuit is measured quantitatively by the quality factor, and the quality factor relates the maximum or peak energy stored to the energy dissipated in the circuit per cycle of oscillation, and that is we define Q, that is equal to 2 pi into peak energy stored in the circuit divided by energy dissipated by the circuit to one period at resonance. And this it is also regarded as a measure of the energy storage property of the circuit in relation to the its energy dissipation property. And in the series RLC circuit, the quality factor is defined as Q equal to 2 pi half L I square, that is the energy stored, divided by half I square R into 1 upon F R, and of course, after modification I square is cancelled out. So, it becomes 2 pi F R L upon R, where of course, F R is the resonance frequency. So, we can call it or Q equal to omega R L upon R, and that is 1 upon omega R C R. So, that is we call quality factor for this RLC circuit, resonating circuit. So, the quality factor is also defined as the ratio of reactive power of either capacitor or inductor to the average power of the resistor at the resonance, and we say Q equal to reactive power divided by average power, and for inductive reactance at resonance. So, Q equal to reactive power divided by average power, that is I square X L upon I square R, that is omega R L upon R, and for capacitive reactance X C at resonance. So, Q equal to reactive power divided by average power, that is I square X C upon I square R, and that is 1 upon omega C R. So, looking here the phasor diagrams of this voltage in RLC circuit, phasor diagram of series RLC circuit is a capacitive when I leads typically below the resonant frequency, the first case, because circuit become capacitive. We already discussed how circuit is capacitive nature. So, in that case voltage your current leads the voltage, and because it is a capacitive circuit, and at resonance both are voltage and currents are in phase, because the reactance is, both reactants are cancel out each other at resonance frequency, and of course, above the your resonance frequency circuit is inductive, and in that case voltage leads the current. I mean, as you can see the in the third case like. So, the voltage across the resistance at F r is V r equal to R I R R, I m equal to R, or V upon R into R, or V r equal to V, and the voltage across the inductor at F r is V L equal to X L I L into omega R L into I m, and that is omega R L V divided by R, or omega R L upon R into V, and that is Q V. So, V you can call it V L equal to Q V. Similarly, voltage across the capacitor at F r is V c equal to X c I c, or equal to 1 upon omega R c into I m, or 1 upon omega R c into V upon R, or V upon omega R c R, or equal to Q V, or V c equal to Q V. So, it depends on the Q that how much voltage will be across your inductor capacitor, and that may be much more than even the supply voltage also. So, Q is the term as quality factor or voltage magnification, and because V c or V L equals Q multiplied by the source voltage, and in series RLC circuit value of V L and V c can be actually be very large at resonance and can lead to the component damage if not recognized and subject to the careful design. And the Q factor at resonance frequency is your Q equal to omega R L upon R and 1 upon omega R C R, or 1 upon R under root L upon C, where the omega R equal to 1 upon omega L C. So, here you can see the your voltage applied is small, your current is substantially large. If current is large, then you can say V L and V c both are quite large, so they are magnifying it by Q into V. I mean, like, so that Q in many cases can be even, you can call it maybe greater than 1. So, that amplify the voltage. So, you can see how the typically in this RLC circuit the effect of frequency variation on voltage across RLC. I mean, you can see it is the voltage across the resistance which is maximum at the resonance frequency. This is the current which is also maximum at resonance frequency, and the V c and V L both are also quite high or maximum at your resonance frequency, and below of course, resonance frequency you can call it V c is more, because your capacitive circuit behave as a capacitive reactance. So, capacitive reactance is higher than inductive reactance, and above resonance frequency the inductive you can call it reactance is high, that is why the voltage across the inductor V L is high. So, coming to define the other terminology called bandwidth and half power frequency, and this we define it as a frequency related to the characteristic. So, in series RLC circuit at resonance maximum power is done, that is P r equal to I max square into R, or where I max equal to V r upon R at resonance. So, bandwidth represents the range of frequency for which the power level in the signal is at least half of the maximum power, and that means the frequency corresponding to half the maximum power, that is P r by 2, or the P r by 2 equal to I max square by 2 into R, or I max upon root 2 square into R. So, bandwidth of a circuit is also defined as the frequency range between the half the frequency point I equal to I max upon root 2. So, you can see here, I mean, how the typically the current, that is maximum current, and how this is the current which is I max by root 2, I mean, like corresponding to half the power corresponding to that, and that is the range of frequency from omega 1 to omega 2, where the your omega r is the resonance frequency. So, this frequency range we call it the bandwidth, like B w, I mean, in the frequency scale like, and that is also similarly shown here, the resonance peak bandwidth and half the frequency bandwidth. So, thus the condition for half power is given I equal to I max upon root 2 and or equal to V upon R into 1 by root 2. So, the vertical line either of side of I indicate that the only the magnitude of the current is under consideration, but the phase angle will not be neglected. So, the impedance corresponding to half the power point including the phase angle is Z equal to R under root 2 at the angle of plus minus 45, and then you know that one side it will be inductive, one side capacitive. So, it one side it will be negative, another side it will be positive like. So, now coming to typically the impedance in the complex form, that will be Z equal to R in bracket 1 plus minus j 1 at resonance, and thus the half power I equal to V upon R in bracket 1 plus minus j 1, and Z equal to R into 1 plus minus J 1. That is virtually the you can call it the current or the impedance at half the frequency of this circuit, series RLC circuit. So, at the half the power point, the phase angle of the current is 45 and below the resonant frequency omega 1 circuit is capacitive and your impedance will be R into 1 minus J 1, and at resonance frequency at resonance frequency at omega 2 above the resonance frequency at omega 2 circuit is inductive and Z equal to R into 1 plus J 1. So, well, now the circuit impedance is given by R Z equal to R plus J in bracket omega L minus 1 upon omega C, that becomes R 1 plus J in bracket omega L upon R minus 1 upon omega C R, and at half the power points that Z equal to R in bracket 1 plus minus J 1, and by comparison of above two equations resulting in, we can call it like omega L upon R equal to minus 1 upon omega R C R is nothing but plus minus 1. So, as we know Q equal to omega R L upon R equal to 1 upon omega R C R. So, now by multiplying and divide by omega R, so we say omega L upon R into omega R upon omega R. So, that minus again 1 upon omega C R omega R upon omega R, just where that comes plus minus 1, and we can say omega upon omega R into Q minus omega R upon omega Q equal to plus minus 1. So, that give you the Q in bracket omega upon omega R minus omega R upon omega equal to plus minus 1, and now for omega 2 we can say Q omega 2 upon omega R minus omega R upon omega 2 equal to 1, and for omega 1 it is the same relation Q in bracket omega 1 upon omega R minus omega R upon omega 1 equal to minus 1. And now for the half power frequency omega 2 and omega 1 are obtained as omega 2 equal to omega R upon 2 Q plus omega R under root 1 plus 1 upon 4 Q square, and omega 1 equal to your minus omega R upon 2 Q plus omega R under root 1 plus 1 by 4 Q square. These give you the frequency in terms of the circuit parameters, and now the bandwidth is obtained. P w is equal to omega 2 minus omega 1, that is omega R upon Q, and that can be written as a bandwidth equal to resonance frequency divided by quality factor, and resonance frequency in terms of omega 2 and omega 1 is omega R equal to under root omega 1 omega 2, and the bandwidth is also expressed as omega 2 minus omega 1 equal to omega R upon Q, that is omega 2 minus omega 1 equal to R upon L, or we can say f 2 minus f 1 equal to R upon 2 pi f L hertz like, or also we can say omega R minus omega 1 equal to bandwidth by 2, that is omega 1 equal to omega R minus bandwidth by 2, that is omega 1 equal to omega minus R upon 2 L radian per second. Similarly, omega 2 minus omega R, that is bandwidth by 2, or omega 2 equal to omega R plus bandwidth by 2, or omega 2 equal to omega R plus R by 2 L radian per second. So, now coming to resonance in series RLC circuit, the conclusion are the voltage which appear across the reactive components can be many times greater than that of supply. So, factor of magnification, the voltage magnification in series circuit is called the quality factor, and RLC circuit accept maximum current from the source at resonance, and for that reason is called an acceptor circuit, and series resonance circuits are used in communication system. Now, coming to the resonance similarly in parallel RLC circuit. So, here we have a source and we have a parallel RLC circuit, the 3 phase with the 3 phase branch consisting resistance, inductance and your capacitance. So, supply voltage is equal to V equal to I Z, where Z is the net impedance of the 3 branches, and in parallel circuit it is simpler to consider the total admittance Y of the 3 branches. Thus, we say V equal to I Z equal to I upon Y, and where we can call it Y equal to G plus 1 upon omega L plus J omega C, or G minus 1 upon J upon omega L plus J omega C, well, or equal to G plus J in bracket omega C minus 1 upon omega L. So, we can say at resonance frequency omega equal to omega R, the net susceptance is 0, and omega C equal to minus omega L, which is 0, and therefore, at the resonance frequency omega R equal to 1 upon under root L C in radian per second. At resonance frequency Y equal to G. So, conductance of the circuit parallel circuit at and I is equal to V g. So, where the conductance G equal to 1 upon R, and we can say the supply voltage magnitude V equal to I upon under root 1 upon R square plus omega c minus 1 upon omega L square, and at resonance frequency omega equal to omega R, we say V equal to I upon under root 1 upon R square plus 0 square, or that is V equal to I into R, and current through the circuit at omega R frequency will be I R equal to V upon R, or you can call it V R V upon R, or you can call I R upon R, or equal to I R equal to I, that is the circuit current like also. So, in that case both the currents I L and I L and I C are equal. So, magnitude of current through the inductor at omega R will be I L equal to V upon X L, that is I R upon omega L or R upon omega L into I or Q into I, and magnitude of current through the capacitor omega R equal to I C equal to 1 up V upon omega X C or equal to I R upon 1 upon omega R C, and that is omega R C R into I or Q into I. So, where Q is the current magnification factor and Q equal to here R upon omega R L or equal to omega R C R. So, we can say current magnification Q is also expressed in terms of inductive or capacitive susceptances, inductive or capacitive reactances and conductance. So, Q equal to 1 upon omega R L G or omega R C upon G or equal to B upon G or R upon X. So, by substituting omega R equal to 1 upon omega C in Q, so we can say Q equal to 1 upon G under root C upon L or equal to R under root C upon L. So, we can say the parallel RLC circuit is the dual of series RLC circuit. Therefore, by replacing RLC in the expression for series circuit by 1 upon R, C and L respectively, we obtain the parallel circuit, and the half frequency, the half power frequency is omega 1 equal to 1 minus 1 upon 2 R C plus under root 1 upon 2 R C square plus 1 upon L C, and omega 2 equal to 1 upon 2 R C plus under root 1 upon 2 R C square plus 1 upon L C under root of that like this. So, bandwidth we can define B W equal to omega 2 minus omega 1, and that is 1 upon R C, and relation between bandwidth and Q is here Q equal to omega R upon bandwidth or omega R R C or R upon omega R L, and we can say half power frequencies in terms of quality factor. So, that is omega 1 equal to omega R under root 1 plus 1 upon 2 Q square minus omega R upon 2 Q, and omega 2 equal to omega R under root 1 plus 1 upon 2 Q square plus omega R divided by 2 Q. Also, we can say omega R minus omega 1 equal to bandwidth by 2 and omega 2 upon minus omega R equal to bandwidth by 2. So, now we can say coming to practical parallel resonance circuit. So, here we have a practical resonance circuit in the sense that you have some definite resistance of the inductor. So, two branch parallel resonance circuit which we also call the tank circuit. So, computation of resonance frequency of a tank circuit. So, the figure shown in the two branch parallel resonance circuit also called the tank circuit, and the total admittance y t of the circuit shown here is y t equal to y 1 plus y 2 equal to 1 upon R s plus j x l plus 1 upon minus j x c, or y t equal to taking kind of here the that is R s minus j x l divided by R s square plus x l square plus j upon x c, and taking y t again R upon R square plus j x l square plus j in bracket 1 upon x c minus x l upon R s square plus x l square. And we can say computation of resonance frequency of the tank circuit is y t equal to R s upon R s square plus x l square plus j 1 upon x c minus x l upon R square plus x l square, and during resonance we at omega equal to omega r the net susceptance is 0. So, that we can say 1 upon second term imaginary term becomes 0, that it means that is 1 upon x equal to minus x l upon R s square plus x l square equal to 0. So, R s square plus x l square equal to omega r l into 1 upon omega r c, or R s square plus x l square equal to 1 upon L upon C. So, R s square plus omega r square L upon C, or omega r equal to under root 1 upon L C minus R s square divided by L square radian per second. So, that is the resonance frequency of your tank circuit with the of course, with the practical tank circuit. So, resonant frequency in hertz is f r equal to 1 upon 2 pi under root 1 upon L C minus R S square upon L square hertz. Now, coming to ideal tank circuit. So, coming to computation of resonant frequency of ideal tank circuit. So, in ideal tank circuit, the series resistance R S is made 0 and the total admittance y t of the circuit shown here R S equal to 0 is your y t equal to y L plus y c. So, that is 1 upon j x L plus 1 upon minus j x c, and that is y t equal to plus j in bracket 1 upon x c minus 1 upon x L. So, at resonance frequency the net susceptance is 0, that is means 1 upon x c minus 1 upon x L equal to 0, or we can say omega r equal to again 1 upon r under root L c, or f r equal to 1 upon 2 pi L c hertz like. So, coming to series resonance in parallel RLC circuit, the lowest with the conclusion, the lowest current from the source occurs at resonant frequency of parallel circuit, hence it is called a rejector circuit. At resonance, the current in the branches of the parallel circuit can also many times greater than the supply current, and the factor of magnification, the current magnification in the parallel circuit is again called quality Q factor, and at the resonance frequency of the resonant parallel circuit, the impedance is wholly resistive. The value of this impedance is known as the dynamic resistance or dynamic impedance, and parallel resonance phenomenon is used in the design of the band stop filters. And now, coming to the summary of characteristic of resonant RLC circuit, we say characteristic is resonant frequency omega r. In series circuit it is 1 upon L C, in parallel circuit also it is 1 upon L C quality factor, that is in series circuit is omega r L upon r or 1 upon omega r C r, and parallel circuit is r upon omega r L or omega r C r, and bandwidth here omega r upon q, as well as in parallel circuit is also omega r L upon q. Half power frequency omega 1 omega t r omega r under root 1 plus 1 upon 2 q square plus minus plus omega r upon 2 q, and of course, in parallel circuit also it is same as omega r under root 1 plus 1 upon 2 q square minus plus omega r upon 2 q. And for high circuit, for quality factor more than 10, omega 1 and omega 2 will be omega r plus minus plus b bandwidth by 2, and this will be your omega r again minus plus bandwidth by 2. So, now coming to dynamic impedance or the dynamic resistance. So, dynamic impedance or dynamic resistance is the resistance offered by the circuit to the input signal under resonance condition, and typically the short answer questions. Now, we can say what is the dynamic impedance in a standard RLC circuit. It is in standard RLC circuit at resonance. At resonance, the net reactance becomes 0, and therefore, the input supply C the only resistance, hence the dynamic impedance is your R. And what is the dynamic impedance in general parallel RLC circuit? In general parallel RLC circuit at resonance, the net susceptance becomes 0, therefore, the input supply C only the resistance, hence the dynamic impedance is equal to R. Then what is the dynamic impedance in an ideal tank circuit? In ideal tank circuit at resonance, the circuit acts like a open circuit. So, because in ideal tank the R S equal to 0, therefore, the dynamic impedance Z dynamic equal to infinite. So, coming to like a typical determine the practice problem, determine the dynamic impedance of parallel tank circuit. So, that is Z dynamic equal to L upon R S into C. Now, coming to some of the numerical problems now, the problem of first we will take on series RLC circuit. So, taking a first problem series RLC circuit. In the circuit of the figure of series RLC circuit, R equal to 2 ohm, L equal to 1 millihenry and C equal to 0.4 microfarad. Find the resonance frequency and the half the power frequency, calculate the quality factor and bandwidth, and determine the amplitude of current at omega r, omega n, omega 1 and omega 2. So, answer is solution is the resonant frequency is omega r equal to 1 upon L under root L C, and that is 1 upon 10 to the power minus 3 into 0.4 into 1 power minus 6. So, it comes 50 kilo radian per second, and the lowest half of the frequency is omega 1 equal to minus r upon omega L plus under root r square to L square plus 1 upon L C. So, that is keeping the value, it comes 49 kilo radian per second, and similarly omega 2 r upon 2 L plus under root r upon 2 L square plus 1 upon L C, and keeping the value of all these, it comes 51 kilo radian per second, and the bandwidth is now omega 2 minus omega 1. that is 2 kilo radian per second, and the quality factor is Q equal to omega r upon bandwidth, that is 50 upon 2, that is 25 in this circuit, and at omega equal to omega r, the I is V m upon r, that is 20 by 2, that is 10 ampere, and at omega equal to omega 1 upon omega and omega 2, I equal to V m upon root 2 r, and that 20 upon root 2 into 2, and that is 7.071 ampere. Now, coming to the question 2 on series RLC circuit, a circuit having a resistance of 4 ohm and inductive reactance of 0.5 Henry and variable capacitance in series is connected across a 100 volt 50 hertz supply. So, calculate the capacitance to give resonance, the voltage across the inductive and capacitance and quality factor of the circuit. So, for resonance 2 pi FRL equal to 1 upon 2 pi RC. So, C comes here by putting the value 1 upon 2 pi into 50 square into 0.5, that comes 20.3 microfarad, and at resonance I equal to V upon R. So, that is 100 by 4, that is 25 ampere, and voltage across the inductor is V L equal to pi FL into typically I, that is 3927 volt, and voltage across the capacitor is the same, V C equal to 3927. So, you can see the voltage across the inductor capacitor is very high compared to what the supply voltage of only of 100 volt, or alternately you can say V C equal to I X C, and that is 25 upon 2 pi into 50 into 20.3 into 10 power minus 6. So, that comes 3927 volt approximately, or quality factor here Q equal to X L upon R, that is 2 pi into 50 into 0.5 by 4. So, this is 39.26, that is responsible for, you can say, amplification or magnification of the voltage across the inductor and capacitor line. So, now coming to the third problem on series RLC circuit, a coil of resistance of 5 ohm and inductance of 1 millihenry is connected in the series of with a 0.2 microfarad capacitor. So, circuit is connected to a 2 volt variable frequency, and calculate the frequency at which the resonance occurs and voltage across the coil and the capacitor at this frequency and quality factor of the circuit. So, you have been given L equal to 1 millihenry, R equal to 5 ohm and C equal to 0.2 microfarad, and FR here is under root 2 pi under root L C. So, it will be 1 upon 2 pi under root 10 power minus 3 into 0.2 into 10 power minus 6. So, it comes 11.25 kilohertz. So, current at resonance is I R equal to V upon R, that is 2 upon 5, that is 0.4 ampere, and X L equal to X C equal to pi F L R and 2 pi into 11,250 into 10 power minus 3, that comes 70.7, and Z L R equal to under root R square plus X L square, it comes 5 square plus 70.7 square. So, that is 71 ohm, and V L equal to V L R equal to I R Z L R, that is 0.4 into 71, this comes 28.4 volt, where the we have a supply voltage only of 2 volt. So, it is amplified like more than 14 times, and V C equal to I R X C equal to 0.4 into 70.7, that becomes 28.3 volt. So, and the quality factor omega R upon R equal to 70.7 upon 5, that is 14.14, that is the amplification factor by which the voltage across the capacitor and inductor get amplified compared to the supply voltage, and this is the typically phasor diagram. So, now coming to question 4, the bandwidth of the series resonant circuit is 500 hertz. If the resonant frequency is 6000 hertz, what is the value of Q? If R equal to 10 ohm, what is the value of inductive reactance, and at resonance calculate the inductive reactance and capacitance of the circuit. So, bandwidth equal to resonant frequency divided by quality factor, hence Q equal to frequency upon bandwidth, and that is given you 6000 by 500. So, bandwidth here quality factor is 12, and quality factor is X L upon R. So, X L will be Q into R, that is 12 into 10 equal to 120 ohm, and X L will be 2 pi L R. So, L is equal to X L upon 2 pi F R, and that is 120 upon 2 pi into 6000, that is 3.18 millihenry, and X L equal to X C, that is 120 ohm. So, X equal to 1 upon F R to C. So, that is 120 ohm, C equal to then 1 upon 2 pi into 6000 into 120, that is 0.22 microfarad. Now, coming to the example 5 for the series resonant circuit shown in figure of RLC, calculate at resonance what are the voltage across the 3 series component RL and C, calculate Q. If the resonant frequency is 6000 hertz, find the bandwidth, and what are the half power frequencies, and what is the power dissipated in the circuit at 2 frequencies. So, at resonance frequency Z equal to R, I max is 20 at the angle of 0 by 4, and that is 5 at the angle 0 ampere, and V R equal to I max R, that is 5 at 0 degree into 4, that is 20 at 0 degree volts like. Now, VL equal to I max into XL, that is 5 at 0 angle into 20 at 90 degree. So, that becomes your 100 into typically at your 90 degree, and VC equal to I max XC, that is 5 into at the angle 0 into 20 at the minus 90. So, that becomes 100 minus 90 degree volts, and Q equal to XL upon R, that is 20 by 4, and that is 4. So, voltage are amplified across X and C by this factor of 4. So, bandwidth is resonant frequency divided by quality factor. So, here bandwidth is 6000 by 5. So, that is 1200 hertz like. So, half the frequencies are at frequency 600 hertz above the and below the resonant frequency of 6000 hertz. So, F2 is 6000 plus 600, that is 6600 hertz, and F1 is 6000 minus 600, that is 5400 hertz, and P max equal to I square, I max square into R, that is 5 square into 4, that is 100 watt, and half the power frequency F1 F2 R, P half power is half P max, that is 50 watt. And now, coming to the problems on parallel RLC circuit. So, with example on 6 in the parallel RLC circuit as shown in the figure, let the R equal to 8 kilo ohm, L equal to 0.2 millihenry, and C equal to 8 microfarad. Calculate the omega R, Q and bandwidth, and find omega 1 and omega 2, and determine the power dissipated at omega R, omega 1 and omega 2. So, omega R equal to under root 1 upon L C, and that is 1 upon under root 0.2 into 10 power minus 3 and into 8 into 10 power minus 6. So, it comes as a 10 to power 5 by 4, that is 25 kilo radian per second. So, quality factor is R upon omega R L, and that is 8 into 10 power 3 divided by 25 into 10 power 3 into 0.2 into 10 power minus 3, that comes 1600, that is the kind of quality factor. So, bandwidth is omega R upon Q, that is 15.625 radian per second. So, now due to the high value of Q, we can regard this as a high quality factor circuit, and hence omega 1 equal to omega R minus bandwidth by 2, that is 2500 minus 7.812, that is 24992 radian per second, and omega 2 is omega R plus bandwidth by 2, that is 25,000 plus 7.812, that is 25,008 radian per second. So, at omega equal to omega R, so y equal to 1 upon R, and z equal to R, that is 8 kilo ohm, and I 0 will be or V upon Z, that is 10 at the angle of minus 90 divided by your 8000. So, it comes like 1.25 ampere at the angle minus 90 degree milliampere. So, since the entire circuit flows through R at resonance frequency, the average power dissipated omega R equal to P equal to half I 0 square R, that is half 1.25 square into 10 power minus 3 square into 8 into 10 power 3, it comes 6.25 millivolt, and P equal to V m square upon 2 R. So, it comes 100 upon 2 into 8 into 10 power minus 3. So, that comes 6.25 watt, and at omega equal to omega 1 and omega 2, P equal to V m square upon 4 R, and that is 3.125 milliwatt. Now, coming to the example 7, a coil of 1 kilo ohm resistance and 0.15 Henry inductance is connected in parallel with the variable capacitor across 2 volt 10 kilohertz AC supply as shown in the figure. Calculate the capacitance of the capacitor when the supply current is minimum, and the effective impedance Z R of the network at resonance and the supply current. So, F R equal to 1 upon 2 pi into under root L C, and so F R square is 1 upon 4 pi square L C. So, C from here you can find out, that is 1 upon 4 pi square L F square, that is 1 upon 4 pi square into 0.15 into 10 power 8, that comes 1.69 nanofarad, and Z R equal to L upon C R. So, that is 0.15 into 1 divided by 7.69 into 10 power minus 3 into 1000, that comes 89 kilo ohm, and I S equal to V upon Z R, that is 2 upon 89 into 10 to power 3, that is 22.5 into 10 power minus 6. So, now coming to the example 8, determine the resonance frequency of the circuit of parallel RLC circuit with of course resistance of the inductor. So, the input impedance is y equal to j omega 0.1, that is plus 1 pi 10 plus 1 upon 2 plus j omega 2, that is 1 plus j omega 0.1 plus 2 minus j omega 2 divided by 4 plus 4 omega square. So, y it becomes y equal to 0.1 divided by 2 plus 2 divided by 4 plus 4 omega square plus j in bracket 0.1 omega minus 2 omega upon 4 plus 4 omega square. So, at resonance omega equal to omega. So, net susceptance is 0, hence the imaginary quantity becomes 0. So, that is 0.1 omega r equal to minus 2 omega r upon 4 plus 4 omega square. So, that comes omega r equal to 2 radian per second. Now, coming to example 9, a parallel resonant circuit has resistance of 100 kilo ohm, inductance of 50 millihenry and capacitance your 2 nanofarad. Calculate omega r, omega 1, omega 2, Q and bandwidth. So, typically answer are 100 kilohertz, 97 kilohertz and 100.2 kilohertz and 20 kilohertz or so. Similarly, typically the problems on another problem. So, these are the different problems typically on this resonance circuit of different natures like also. So, these are some of the kind of the typically the quiz problem which you can probably go through, and these are the references from which we have taken the material of this lecture, and thank you very much.